Welcome to this explainer from Forge College. Now, you might remember in our last lesson on trust dynamics and incentives, we talked about how social reputation basically acts as the glue holding traditional systems together. But as we continue our track on blockchain fundamentals, specifically looking at the philosophy and practical value of decentralization, we're taking a massive leap forward into today's topic: trustless systems and practical implications. Usually, when you do business, you're trusting a human counterparty. But what happens if that counterparty suddenly decides to just, pack their bags and run off to a tropical island with all your assets? It's a classic problem, and frankly, it's really not ideal. So what if we could architect systems where that simply isn't an option? That is exactly what we're going to explore today.
Okay, let's dive into this. We're going to unroll this full topic like a master architectural blueprint. We've got 5 stops today: the trustless myth, 4 practical guarantees, trust in the real world, code under the microscope, and finally, the redistribution trade-off.
All right, Section 1, the trustless myth. Let's unpack this concept. I want you to imagine trust as a massive, incredibly heavy box that you literally have to carry around every single time you want to transact online. You have to trust the bank, trust the vendor, trust the payment processor. It's a lot. Now, the word trustless gets thrown around constantly in the Web3 space, and it makes people think this heavy box just magically vanishes into thin air. Well, I'm here to tell you it doesn't. Trust doesn't just evaporate. What we're actually doing in a trustless system is putting that heavy box on wheels, specifically the wheels of cryptography and code. So you don't have to carry the whole weight on your own back anymore, but make no mistake, the box is definitely still there.
When we actually define the buzzword trustless, what we're talking about is a set of technical properties that rely on predictable cryptographic verification rather than discretionary human action. So we are completely popping the myth that it means the absolute absence of trust. It's actually a shift in dependencies. Instead of trusting a person who might, just be having a bad day, make a silly error, or have some hidden agenda, we're trusting math, distributed consensus, and explicitly observable state transitions.
Moving from that high-level philosophy into the concrete mechanics, let's jump to Section 2 and look at 4 practical guarantees that actually replace traditional handshakes and paper contracts. Now, what's really interesting about this matrix here is that every single structural guarantee we build introduces a distinct, inescapable limit. Take a tamper-evident ledger, for example. It's brilliant. It completely prevents the silent rewriting of history without anyone noticing. But it requires massive persistence and absolute resistance to majority collusion. Or consider deterministic execution. It entirely removes the need for a human executor, but then it relies 100% on the fidelity of the inputs. The reality is, you simply cannot get the structural guarantee without explicitly accepting its engineering limitation.
And that brings us to a vital distinction between cryptographic guarantees and operational guarantees. Cryptographic guarantees are based purely on math and internal consistency. They are rigid, unforgiving literalists. Math doesn't care about your feelings. It just proves that a sequence of bits is mathematically consistent. Operational guarantees, on the other hand, deal with data fidelity and honest oracles. This is where we crash right into messy operational reality. Cryptography can absolutely prove a digital signature is valid, but it cannot, on its own, guarantee that the real-world data feeding into the system, like the price of an asset, the weather in London, or whether someone tripped over a server cord, was actually honest and accurate to begin with.
So how does all this theoretical framework dictate our architectural design choices in practical, everyday applications? Let's get into Section 3, Trust in the Real World.
Here we've mapped out 3 very common structural scenarios where flaky human agents are swapped out for solid, protocol-level guarantees. First up, atomic settlement. These are all-or-nothing swaps where the protocol enforces that either both sides receive their assets or nobody does. You don't trust the counterparty at all. You trust the smart contract. Second, automated escrow. This is where the code physically holds the funds and releases them only when predefined conditions are met. And third, data-driven triggers, which are super common in lending, where contracts will automatically liquidate collateral based on incoming price feeds. And as you might know, we frequently explore these exact structural patterns in our other Forge College courses. But what does this mean for your crypto wallet? Well, it means human discretion is gone, but it introduces an absolute, total reliance on the underlying code and data feeds.
So, let's put this reliance to the test. Section 4, Code under the microscope. I invite you to lean in and act as a technical auditor with me right now. Let's hunt down those new hidden trust boundaries we've been talking about in a real simple escrow smart contract.
Consider this simple version header right here: Pragma Solidity.
It looks completely harmless, right? Just a standard piece of syntax. But structurally, this represents a massive, hidden trust assumption. You are trusting the software compiler to perfectly translate human code into machine code without introducing any undefined behaviors. Think about that. If there's a flaw in that developer toolchain supply chain, your entire trustless system is compromised before it even runs.
Moving down the blueprint, we see the deployment phase, a constructor asking for payee and arbiter addresses. During deployment, you are heavily trusting the human deployer. Why? Because if they make a typo, it is completely irreversible. There is no 1-800 customer service hotline to call and reverse a transaction on a blockchain. You are entirely trusting human accuracy at the exact moment of deployment to not lock those funds away forever.
And here is the core engine of our contract, a release function. This deterministic rule is exactly what replaces our untrustworthy human escrow agent. It enforces that funds only move to the payee when properly authorized. But, and it's a big but, because code is law here, any logic flaw means the funds are either permanently trapped or worse, drained by a hacker. The code has to be absolutely flawless.
So the crucial point is that we haven't eliminated trust at all. We've just moved it around. We now face totally new trust boundaries. Concentrated arbiter roles in escrow agreements, the absolute unforgiving demand for code correctness, those invisible toolchain supply chains, and network liveness just to actually process the transactions. We have simply traded traditional counterparty risk for a brand new set of highly concentrated technical dependencies.
And this brings us to Section 5, our final architectural takeaway, the redistribution trade-off. The entire concept of reducing trust is actually a masterclass in trade space optimization and the clever redistribution of risk.
I want to deeply emphasize this core takeaway right here. Trustless does not mean trust-free. Because trust is just redistributed, we as engineers and users have to build and expect conservative guardrails. We need multi-signature processes for arbiters, we need multi-source data for our oracles, we need on-chain time locks, and really robust fallback mechanisms. You are managing the exact same weight of trust, but you're intentionally distributing it across a different, much more transparent set of architectural pillars.
Which leaves us with this final, genuinely provocative question. If trust is now decentralized and shifted away from individuals over to protocol-level code, who actually governs that code? When a critical contract needs upgrading or a sudden bug is found, who actually holds the keys? Well, that is exactly what we are going to tackle in our next module on measuring centralization. Thank you so much for joining me for this explainer. To continue your learning journey and explore more amazing Web3-related topics, make absolutely sure you visit forge.college. Keep exploring, and I'll see you in the next one.